Does mathematics ever feel like just a huge collection of totally disconnected islands? You've got algebra over here, geometry way over there. It can feel, well, pretty overwhelming. Today, we're diving into a book that's basically a map, a guide to the entire world of modern math, and it shows how all those islands, they're actually part of one massive, interconnected continent.
In this whole journey, it really starts from a place I think we can all relate to. The author just had this hunger to see the big picture of math, but there was no clear path to follow. So this explainer, which is based on their work, is the map they wish they had. It's the solution to that problem of just getting lost in all the details.
So, what is that problem? Well, it's exactly what the author calls it, trying to navigate the sprawling expanse of mathematics. It's so easy to get lost, right? You dive deep into one topic, and you never see how it connects to anything else. But what if there's a hidden structure, a logical path that actually links it all together? Well, that's what this is all about. We're going to uncover that hidden map.
So, our journey starts with the absolute bedrock of modern algebra, the group. It's this simple but incredibly powerful idea that really everything else is built on top of.
So, what is a group really? Well, at its core, a group is just the language of symmetry. Seriously, that's the key idea. Think about a simple square. You can rotate it 90 degrees, 180, 270, and it still looks like the exact same square, right? Well, those rotations, those actions that preserve the shape, they form a group. It's a way to mathematically capture this idea of sameness, even when you're changing something.
And when you get down to it, the formal idea is surprisingly simple. A group is just a set of things plus a single operation, like addition, and as long as that operation follows a few basic rules, like having an identity element and inverses for everything, boom, you've got a group. That's our fundamental building block.
And the cool thing is, you're already familiar with tons of groups. Take the integers with addition. That's a perfect example. You add any two integers, you get another integer. 0 acts as the identity. Every integer has its negative, which is its inverse. Same thing goes for rational numbers and real numbers. Or if you take all the non-zero numbers, they form a group with multiplication. So it's this very abstract idea, but it has really concrete roots.
Okay, so we have our first building block, the group. Now, what happens if we start adding more structure, more rules? Well, that's how we build up the entire world of modern algebra.
And the progression is actually pretty elegant. We start with a group, which has just one operation. Now, if we add a second operation, like multiplication, we get something called a ring. Then, if that ring also lets us divide by any non-zero element, we've leveled up again to a field. It's like a ladder, and with each step, we're adding more structure and more power. To make this idea of a ring a little more real, just think about polynomials. You can add two polynomials together, and what do you get? Another polynomial. You can also multiply them. But can you always divide them and still end up with a nice, clean polynomial? Nope, not always. And that's exactly what makes them a ring, but not a field. They have the two operations, but division isn't always guaranteed.
All right, so far we've been talking about rules for, combining numbers and symbols. But this is where our map takes a really fascinating turn. We're about to connect all this abstract algebra to the very tangible world of geometry, shapes, and spaces.
And this is the million-dollar question, right? We've built this whole algebraic machine with groups and rings and fields. So what? I mean, how do these rules for symbols actually help us understand the world of shapes and space? Well, here's the incredible answer. Those algebraic structures we just talked about, they are the absolute foundation for how we understand space. Linear algebra, the study of vectors and transformations, it's built directly on the rules of a field. And topology, which studies the deep essential properties of shapes, it also relies on this algebraic groundwork. The huge insight here is that the rules of algebra are the rules that govern space. Okay, so we've got our algebraic rules, and we've got our connection to space. But there's one last huge ingredient missing from our universe: motion, change, and that really tricky concept of infinity. And this brings us to the realm of analysis, the part of math that really brings everything to life.
And the one big idea that powers all of analysis is continuity. It's all about studying smooth, unbroken change. It doesn't matter if we're looking at functions on a simple number line or out on the complex plane, the central theme is always about understanding what happens when things change smoothly, without any sudden jumps or breaks.
I mean, this just captures the entire essence of calculus without a single messy formula. The whole idea of the derivative, which measures change, is this. If you take any smooth curve and just zoom in far enough, I mean really, really far, it's gonna look like a straight line. The derivative is simply the slope of that line. It's the local, instantaneous rate of change. That's it.
Okay, but this is where things get wild. When we jump from the real number line into the complex plane, the rules just completely change, and in some really counterintuitive ways. So check this out. In the real world, a function can be differentiable, but maybe it's not perfectly smooth. In the complex world, no way. If a function is differentiable even once, it is automatically infinitely differentiable. It's perfectly smooth. It's a different universe. There's a reason the author calls this field remarkable and beautiful.
So there you have it. We've journeyed from the absolute simplest rules of algebra all the way to the mind-bending worlds of topology and complex analysis. We've basically built a mathematical universe. Now, let's circle back to the map that guided us here in the first place.
So who is a map like this really for? Well, as you can see, it's pretty much for everybody. It's for students, it's for scientists, it's for anyone who just wants a refresher, or really anyone with a curious mind who wants to see how this incredible world of mathematics actually fits together.
And the whole point of this framework is to be first coherent, to show all those connections we've been talking about, and second, efficient, to get straight to the important ideas. It's all about telling one unified story. And this is not just some abstract academic exercise. This is the crucial point. These are the actual tools that working mathematicians and scientists find the most useful. This is the essential toolkit that has really stood the test of time. So, we end right where we began, with this idea of a journey. We've laid out the map of this incredible intellectual landscape, from the foundational rules of algebra to the highest peaks of analysis. The only question left is, where do you want to go next?